Alright, so this is the third part in our deep dive on determinants and inverses, and we're finally making a lot of progress. But for the new viewers, let me just recap what we've done. So we've looked at basic properties of determinants. We found determinants for 2x2 case, found determinants for 3x3 case, and then we generalized it. So we generalized it for the n/n case, right? And by looking at these, we found actually how to take the determinant of something by taking the Laplace expansion of it, right? And the way we found this is by writing the determinant of, say, matrix M as AA plus BB plus CC plus ... for the n/n case. And by looking at these coefficients A, B, C, we notice that we can write the determinant as M star M equals determinant of M times the identity, right? And from that we saw that the inverse is nothing more than 1 over the determinant of M times M star. And then we went on to show that for a generalized n/n matrix, for the 2x2 case, we can write the determinant has 2 factorial terms, right? For the 3x3 case, the determinant has 3 factorial terms. And for the n/n case, the determinant has n factorial terms. So this led us to find the formula for the determinant of some matrix is a sum over permutations. And of course, we have to include the sign of the permutation is going to be a permutation over all the rows. So this, all the way m, Pn. Okay, and this was our big formula. The determinant is nothing more than n factorial terms, which are permutations over the rows. Okay, and then as an example, we did a 2x2 case, and we saw that it actually does work out. And I'm assuming a lot of you, your minds were blown, which mine was too. Okay, and then we found a bunch of rules for the determinant in that, just to name a few, if 2 rows of the matrix are the same, then the determinant is 0. We can multiply one row and subtract it from another, which is basically the same thing as doing elementary row operations, and that makes the determinant the same. And also, what else? The determinant of a matrix is the same as this determinant of the transpose. Just a bunch of great stuff. But now, I want to introduce one more useful concept before we get into the inverse. And this useful concept we're going to need later, and it's actually, so let me just write here, aside. This is actually really cool. I think you guys are going to like this a lot. So, the determinant of M, we can write it as this. Determinant of M can be written as like this. Epsilon. Epsilon I, J, K, all the way to M, and this epsilon I'm going to talk about right now. Let me just write down the formula. M I P M J Q M K R all the way to M MS equals epsilon P Q R ... S, the determinant of M. Okay, now this is a very neat formula. What is epsilon? Epsilon PQR ... S is known as the anti-symmetric. Well, some people call it a tensor, some people call it a symbol. I won't confuse you guys, so I'll just write symbol. So this is the anti-symmetric symbol. And the way it's defined as is like this. Epsilon, if we have a collection of terms L and M, is equal to negative epsilon if we switch them, and it's also equal to 1. Oops, sorry, I didn't mean that. So if we have a collection of terms L and M, if we have two terms L and M, and we flip them, as we did here, epsilon, the anti-symmetric symbol, flips sign. Okay, I'll give you an example of this in a second. I just want to write down the general rules. And 2, if we have epsilon 1, 2, 3, all the way to, like, say, n, that's equal to 1. Okay, and so let me give you some examples of this. So examples. So standard examples, epsilon 1, 2, 3 is equal to 1, right? Because this is just that. And then epsilon 1, 2, 3 is the negative of epsilon 1, 3, 2, right? Because we flipped them. If we flip them, then it takes on a negative sign. And this is the same as epsilon 2, 3, 1. It's cyclical. Same thing as epsilon 3, 1, 2. And this is all equal to 1. And also this means that epsilon 1, 1, 2, if we have a repeated index here, 1, 1, 2, this is equal to 0. Because, why? Well, epsilon 1, 1, 2 would have to be the same as epsilon 1, 1, 2, but with a negative sign. If we flip the first and second index, and that would have to be the same. But that's only the same if epsilon 1, 1, 2 is 0. Okay, there's no other way that this could be valid if it's not equal to 0. So now back to our equation. What is this beast? What is this beast over here? What is this beast? Let me just box this guy. Alright. What is this beast? Alright, so let's do an example, of course. Let's do for a 2 by 2 case. So 2 by 2. Okay. For the 2 by 2 case, we have this. First thing to note, by the way, is that you see we have a collection of dummy indices. We have I, J, K, K, all the way to MM. And Einstein's summation convention, so this is using the Einstein summation convention, is that I is summed, J is summed, K is summed, right? So in our example here, for the 2 by 2 case, we're going to have epsilon, P, and Q, right? The determinant of M is equal to, well, since it's 2 by 2, we're going to have epsilon ij, and then what else? We're going to have MIP, MJQ. So MIP, MJQ. And I just said that this is summed because it's a dummy index. So this is the same thing as saying sum over I, sum over J of epsilon ij, MIP, MJQ. And just for clarity, we know that P and Q are both free indices because they appear both on the right-hand side and the left-hand side, and they are not being summed over. Okay, so now let's assume that, let's take P, Q equal to 1, 2. So we get rid of this guy. And then epsilon 1, 2 is obviously 1, right? Because it's symmetric. I mean, it's in order, so that means it's equal to 1. So this means that the determinant of M is nothing more than the sum over I, sum over J of epsilon ij times mi1, P is 1, and mj2. Q is 2, right? So, okay, let's take the sum. So this is going to be epsilon 1, 1, m11, m2, m11, m12, plus epsilon 1, 2, m11, m22. Oh boy, we're going to have 4 terms here. Plus epsilon 2, 1, m21, m12. And then lastly, what are we going to have? We're going to have plus epsilon 2, 2, m22, m22. I ran out of space, sorry. Okay, but we know that if epsilon has the same, if there are two numbers that are the same, it's 0. So this guy is 0, and this guy is 0. So we're just left with epsilon 1, 2, m11, m22. I think you guys could already see what's happening here. m21, m12. And this guy is 1. This guy is negative 1, right? Because we have 2, 1. So we flip the numbers. So we have to change the sign. So this is nothing more than n11, m22 minus m21, m12. And this, as we've seen for the millionth time already, is indeed the determinant of a 2 by 2 matrix. So, we have another way of writing the determinant. That's cool. Okay. I mean, there's really no use to this yet until we get to some more advanced topics later. But this is pretty cool, right? You guys learned a new symbol, anti-symmetric symbol. Its properties here, and it's actually used to do the determinant. And we got some practice using the Einstein summation convention, right? We summed over I and j. Okay, that's pretty cool. But now to the main story. Let me just save this guy real quick. So this is deep dive 4A. Superb quality, of course, as always. All right, let's do it. You guys are gonna get mind blown right now. All right, Cramer's formula. All right, so to recap, we've started our hunt for the inverse, right? We took this linear system, we did the poor man's approach. We found the determinant. We found that the inverse greatly depends on the determinant and like that, those uppercase letters. And then we found that through our goal to find the inverse, we came across the determinant and we studied the determinant quite a bit. We found that the determinant is nothing more than, the permutation, the sum over permutations of the rows. And that is also, it can be written in terms of this anti-symmetric symbol, which is pretty neat. We've found some properties of determinants, but now that we've done the determinants, it's time to find the inverse. So Cramer, also the name of my neighbors, found this very cool formula for the inverse. So the ijth component of the inverse is equal to 1 over the determinant of the matrix times -1 to the I plus j times the determinant of what I'll call m tilde of j slash I slash. Okay, so this is Cramer's formula. And what is m tilde? M tilde is this n minus 1 by n minus 1 matrix found by crossing out the, so here you see the jth row, and here is the ith column. So that's why I wrote the slashes here, because they're supposed to mean actually that you have to cross out the jth row and the ith column. Okay? So this is the formula. This is the components. These are the elements of the inverse. So let's try it out for a 2x2 matrix. 2x2 matrix. Okay? 2x2 matrix. Okay. So let's say our matrix M is A, B, C, D. Alright? M -1. Let's start out with the first row and the first column. This is going to be 1 over the determinant of M. I'll just write determinant of M. -1. So this is 1 plus 1, so -1 squared. And then determinant of M tilde, and then J slash I slash. So we slash the first row and slash the first column. So slash the first row, slash the first column. We're just left with D. So this is -1 squared is just 1. This is just nothing more than the determinant of D over the determinant of M. And the determinant of a number is just that number, so this is going to be D over AD minus BC. And if you recall, the inverse for a 2x2 matrix is nothing more than 1 over the determinant of M times D A negative B negative C. So this is indeed correct. This corresponds to that element right there with the appropriate coefficient. So this is actually pretty crazy. So from this, we can see very clearly that the inverse of a matrix is nothing more than the ratio of determinants. The inverse of a matrix is nothing more than the ratio of the determinant of the matrix found by crossing out the jth row and the ith column divided by the determinant of the whole matrix. It's crazy if you think about it. It's really crazy. Inverse elements are nothing more than determinants of lower dimensional matrices with appropriate coefficients. The inverse is just the ratio of determinants. That's all it is. And that's the profound insight that I want to share you guys in this deep dive. We started off, you guys might have known how to take the inverse of a matrix using some proven methods. Okay, that's all good, but that doesn't really show you the deep insight into what an inverse of a matrix is. So we've taken our deep dive into determinants. We've found the Laplace expansion, right? We've actually derived the Laplace expansion. And then this all culminates into Cramer's formula with the inverse being equal to the ratio of the determinants. So I really hope that this gave you a lot more insight into how everything works and how linear algebra is such a very interconnected theory. It's a very rich and deep theory. And this is a very nice result. I mean, come on, just look at it. It's beautiful, right? Okay, so this concludes everything for now. And if you're confused by anything, just rewatch it and then write any questions you have in the comments. I'll be sure to respond as soon as possible. But I hope this makes sense. If you just look at this from the beginning, this looks extremely complicated. We have some kind of m tilde, -1 to the I plus j, but we've started from the beginning with literally linear equations, and we've managed to get all the way here, and I think that's pretty remarkable. Okay, so I'm signing off. Have a good one.